Greetings! Here we go. The next series of lectures is important and full of content. These lectures also serve as a perfect review of many of the concepts and computations we've introduced in these other videos. Remember, this is the roof of our chemistry house. Much of the structure had to be built to get to this point. This series will focus on introductory concepts in chemical processes and changes of state. Hey, we commonly refer to these as chemical reactions. A chemical reaction describes the process of taking an initial state with either atomic, ionic, and molecular compounds to a final state with different atomic, ionic, and molecular compounds. Another way to think about a chemical reaction is that it is a process in which the arrangement and bonding of atoms in the initial state are different than in the final state. Many times, when a chemical reaction has occurred, there is some observable evidence to accompany the changes when the atoms rearrange themselves into these new compounds. Sometimes you see the formation of a new solid, called a precipitate. You may see color changes or the evolution of a gas. Many times, the reaction will be accompanied by some absorption or emission of heat, endothermic and exothermic processes. And one possible change might even be the emission of energy in the form of light. Now, just because we observe these effects does not mean a reaction happened. We know that physical processes can also be endothermic or exothermic, and we know that atoms, if excited, will give off light to produce line spectra, but will not change their arrangement within a compound or system. Also, we must be aware that sometimes we won't see any visual evidence that identifies that a reaction occurred. The reason could be because of the subtle nature of the reaction, or the small scale and concentration of the reactants and products involved in the chemical process. In these instances, sometimes the only way to recognize the presence of a reaction is to use ultra-sensitive spectroscopy and other high-resolution scientific measurements to identify and characterize different compounds that might have formed during the chemical process. The first thing we want to be able to do when identifying reaction processes is to write them down in the form of chemical equations. Let's look at a typical reaction. Ethanol liquid C2H5OH is burned completely in the presence of oxygen gas to form carbon dioxide gas and liquid water at 25 degrees C. This reaction is an example of a very common process called a combustion reaction of an organic molecule. If one of the reactants is an organic molecule containing carbon, oxygen, and hydrogen in a complete combustion reaction, the other reactant is assumed to be oxygen gas. The products of a combustion reaction are assumed to be carbon dioxide gas and water. Now at 25 degrees C, the water will be in the liquid form, but you will often find it written as a gas in some texts. This would be true if the reaction is being run at elevated temperatures. So let's take chemical language describing the reaction and transform the words into an actual chemical equation. Step 1. The first thing we need to be proficient at is nomenclature. Many times a reaction will be described by chemical names, and we have to translate those names into chemical symbols and compound formulas. In this example, we have 4 chemicals. One has been identified for us, ethanol, which is C2H5OH. We have our other reactant, our old friend oxygen, O2, a gas which in its pure form must always be assumed a diatomic molecule. Remember your diatomic gases, okay? And turning to the products, we have carbon dioxide, which is CO2, and last but not least, water, which is H2O. Step 2. For each chemical, we must also identify and write down its physical state. The most common states we will deal with are gases, written as G, liquids, written as L, solids, written as S, and aqueous solutions, AQ, which are solutes dissolved in water. As an example of an aqueous chemical, if we have sugar or a sodium cation dissolved in the water, we would write them as shown. In this example, at 25 degrees C, we add the liquid identifier to the ethanol because the problem said it was a liquid. Oxygen is a gas, since oxygen in its pure form is almost always a gas at normal temperature and pressures. Carbon dioxide is a gas, and the H2O is in its liquid state. Step 3. We draw the reactants on the left side of the chemical equation, and products will go on the right. Usually we draw an arrow left to right to do the connector, unless we are told it is an equilibrium reaction. For an equilibrium reaction, we write a double arrow. We also can place critical reaction conditions, heat, catalyst, light, solvents, temperature, above or below the connector. Now, the last step is critical if we want to do anything useful with the chemical reactions, such as quantifying amounts of reactants or products, or discussing things like mechanisms of the reaction. Step 4. We must balance the chemical reaction. We will assume that the conservation of mass applies when dealing with ordinary chemical reactions. So each atom that appears in the initial state must also be present in the final state. In other words, the same number and elemental types of each atom in the reactants must be present in the products as well. As an aside, but something we won't bother with right now, is that the total charge of the reactants must balance with the total charge of the products. We call this charge balanced. A method for balancing chemical reactions is outlined in Tro's Introductory Chemistry book that we've continued to reference at the end of all our lectures in the bibliography. We will follow the method outlined in that book quite closely in this slide. So far, we have the following rough and unbalanced chemical reaction for our ethanol combustion problem at 25 degrees C. It is important to remember that when balancing chemical equations, to never change the subscripts on any of the compounds, because that changes the identity of the compound. The only values we will change to fix our balancing problem is the stoichiometric values in front of the compounds. Currently, even though it's not written, we can assume a 1 is present in front of all the compounds. So let's first list the rules for balancing reactions and then apply them to our example. If an element occurs in only one compound on both sides of the equation, balance it first. If there is more than one such element, balance metals before nonmetals. If an element occurs as a free element on either side of the chemical equation, balance it last. Always balance free elements by adjusting the stoichiometric coefficient on the free element. If the balanced equation contains coefficient fractions, change these into whole numbers by multiplying the stoichiometric coefficients of every compound in the chemical equation by the least common multiple of the fractions. Most of the time, there will be only one fraction, so just multiply the whole equation by the denominator of that fraction. Check to make certain the equation is balanced by summing the total number of each type of atom on both sides of the equation. Now, we can balance our ethanol combustion equation. Let's strategize the order in which we will balance the atoms in the example reaction. For our ethanol combustion reaction, we see that carbon shows up in the ethanol and the carbon dioxide, and the hydrogen atom shows up in the ethanol and water. So carbon and hydrogen atoms show up on both reactant and product sides of the equation. Which do we balance first, the carbon or the hydrogen? Well, I tend to always do the heavier and more metallic elements first. So we'll balance carbon first, then the hydrogen. We also need to notice that oxygen is a free element all by itself on the reactant side. So the stoichiometric coefficient in front of the oxygen gas will be the last number we consider when balancing the atoms in this reaction. We begin by balancing the carbons. We have 2 carbons in the ethanol, so it's a simple fix to balance them by changing the stoichiometric number in front of the carbon dioxide molecule. We will change the 1 to a 2 in front of the CO2 molecule to balance our carbon atoms on both sides of the equation. We next deal with the hydrogens, utilizing the new equation we obtained after balancing the carbon atoms. We see that we have 6 hydrogens in the reactant side of the equation and only 2 in the product side. Again, the easiest thing to do is to balance the hydrogens, is to increase the stoichiometric coefficient in front of the water molecule to 3, thus giving us a total of 6 hydrogens on the product side. Now finally, we can deal with the oxygen atoms. According to the second rule, since the oxygen is a free element on the left side, this will be the only stoichiometric coefficient we will have to change to balance oxygens in our equation. Right now, we have 3 oxygen atoms in the reactants and 7 oxygen atoms on the product side. We need 4 more oxygen atoms on the reactant side. So if we place a 3 in front of the oxygen molecule, this should do it for us, giving us 7 total oxygen atoms on the reactant side. Our combustion reaction up to this point is shown on the slide. In this example, we don't have fractions, so we don't have to use the third rule. We are not done. In this kind of problem, it's so easy to check our work to see if we have the right solution, so it would be unwise not to. So let's check our balancing. We have 2 carbons on each side, 6 hydrogens on each side, and 7 oxygens on each side. Check. Let's do another example. A piece of iron reacts with hydrochloric acid to form an aqueous ferric chloride solution and hydrogen gas. This is a very common and quick way to produce hydrogen gas, dropping metals in concentrated acids. Acids, unless stated otherwise, can be assumed to be in the aqueous form. And as always, we know that the hydrogen's elemental form is a diatomic gas. The basic unbalanced reaction can be written as shown. According to the rules, we'll balance the following atoms in this order: the iron, the chlorine, and finally balance hydrogen via the stoichiometric coefficient on the H2 since it's a free element. The iron is already balanced, so we're done. To balance the chlorine atom, we put a 3 in front of the hydrochloric acid to balance the 3 Cl atoms on the product side. Now we count hydrogens. We have 3 on the reactant side and only 2 on the product side. Remember, we balance hydrogens by only changing the H2 stoichiometric coefficient, since it's a free element there. The way we do this is by putting a fraction, 3/2, in front of the H2 molecule. 3/2 times 2 hydrogen atoms in the molecule give us 3 hydrogen atoms on the product side, balancing the hydrogens on the reactant side. This equation is a perfectly acceptable form of the reaction for doing quantification work, but not the best description of what seems to be happening mechanistically, since it's hard to envision having half of a molecule. So we move on to the application of the third rule, which requires us to multiply the whole equation by 2, which is the denominator of our fraction on our H2 product. The final balanced reaction without any fractions follows. Now we check our answer. 2 iron atoms, 6 chlorine atoms, and 6 hydrogen atoms on each side. Check. Okay, great start. At this point, we can write down chemical reactions and balance them. Practice on the following problems to lock the balancing rules into your memory banks, okay? Catch you later.